Hi everyone! Today I want to talk about the internet. There are so many questions that can be asked, like what is the internet? How does it even work? Or how am I able to connect to the internet? Or how my laptop or my phone can reach YouTube so I can watch this video right now? And the fact is that in this video you will find answers to all those questions. And I want to go today quite deep into this subject. It will not be material where you will hear, oh, internet is a network of networks. No, today we will explore what exactly is in that cloud, what kind of devices move that traffic, and how that traffic even knows where to go and how to find that YouTube server or Google service or any other server we want to access. So let's get started. And let's start from the very beginning. What does it even mean that you use the internet? You are using internet right now as you are watching this YouTube video, and that's just one use case. It means that you probably typed in your browser something like youtube.com, and then that browser that is installed on your laptop or your mobile phone or PC is connecting to YouTube server, and it's pulling this video right now from that YouTube server. So it's done by using your public IP address you were given by your internet service provider or ISP, and it's connecting to a YouTube server that also has another public IP address. And some of you might think, hey, I don't think I have any public IP addresses. Well, the truth is, yes, you have. And you can easily check what is your public IP address by typing, let's go to Google and just type, what is my IP? And then, well, first link from the top, it will tell you what is your current public IP address. And if you are on Linux or Mac, you can also use the terminal for that. And just type curl ifconfig me, for example, and it will show you exactly the same information. It will show you your public IPv4 IP address. And this is mine. And this is the address you can use in that public network called the internet. And this public IP address is usually assigned to one interface, wide area network interface, on your device that you were given from your service provider. And that provider, that ISP, controls that. So that's why you might not even be aware what the public IP is. It also means that that ISP can also change this address every now and then. So maybe for some reason tomorrow you will be assigned different public IP address when you check it again. But it doesn't really matter, because as long as you have public IP address, it doesn't matter what it is. Simply having one means that you can browse the internet. And if you wonder what is the IP address of the YouTube then, well, it's also very easy to check that. You can type here nslookup youtube.com, and that will give you the public IPv4 address of youtube.com. So we are simply going from this public IP address to that one. And we will talk about this server side a little bit more later on in this video. But for the time being, you have to just be aware that when you type youtube.com, your browser really wants to go to this public IP address rather than this name. But for now though, let's think what else we can do on this internet. So except of watching the YouTube, maybe you want to Google something. Well, we just did, didn't we? So you can go to google.com. This is yet another server. But maybe you want to buy something online. Or maybe use WhatsApp or Messenger to contact your friends or family. Or maybe you want to play a game online. All those use cases have common denominator, and it's the fact that we are going from one public IP address to another public IP address. And behind that public IP address is a server that serves whatever needs to be served. So yeah, hope that's clear by now. We simply go from one public IP to another. And you might think now, if there is a public IP, is there also a private IP address? And what even that IP address is exactly? So to answer the first question, yes, there are public IP addresses and there are private IP addresses. And we will explore them in a minute, but let's start from even more basic question. What actually IP address is? So IP means Internet Protocol, and IP address, or Internet Protocol address, is kind of a unique address that can be assigned to a resource in the Internet. So you can think of IP address as if it was your home address. If somebody sends you a letter They have to know your address, and you can be sure it will be delivered correctly because there is only one such address in the entire world. And the same is true with the IP address. It's simply a unique, one and only address that exists on the internet, and if you have that public IP address, you can be sure that nobody else will use it because each such address is unique, just like your home address. There are no exactly the same two home addresses. There is a little twist though in this story, because we have more than one version of IP addresses. So maybe you probably saw already, you saw that it told us IPv4 address is this, IPv6 not detected. Why does it say it? As you might guess, IPv6 is a newer version of Internet Protocol address. And that's exactly what it's called, IPv6. In fact, there was an entire range of versions of IP addresses. So if we go to Google again and type something like versions of IP addresses, you can see that currently there are two types, IPv4 and IPv6. But if we go to Wikipedia, maybe IP versions, or let me just go to IP version numbers. This is really what we need. List of IP version numbers. You can see IPv4 is here and IPv6 is there, but in fact we had all versions from IPv0 up to IPv15, but they're all either obsolete or abandoned or unassigned. So we're left with IPv4 and IPv6. But why do we even have two versions and not one only? And that's mainly because IPv4 was created in 1980s and it's only 32-bit long. And that bit is kind of a shortcut of binary digit. And you will see binary digits a lot in IT because that's how computers work. Because they use electricity and on is simply equivalent of 1 and off is equivalent of 0. There are no other signals that computer can work with. So IPv4 address is something that computer can read as a string of 32 electrical impulses. But to make it more readable for us humans, it was decided that we will divide these impulses into 4 octets, so 4 chunks, where each chunk will consist of 8 impulses. And then we convert each of those chunks to decimal numbers. So if you convert each of those octets to decimal, you will see that the lowest number we can get is 0, because it's 8 zeros in binary, and the highest number we can get is 255, which is 8 ones in binary for each of those octets. That means the lowest IPv4 address we can have is 0.0.0.0, and the highest can be 255.255.255.255. But that also means the number of unique IPv4 addresses is 255, you have to multiply it like 4 times, which is over 4 billion addresses, and in 1980s it was considered insane. Back then there was only few computers available in 1982, let's say, and nobody ever thought that you could ever run out of public IP addresses. But it changed very quickly though when the internet became extremely popular, and people in 1990s already realized that this number that seemed so huge, like 4 billion of available unique IPv4 addresses, might become problematic sooner rather than later, because they saw how quickly they have to assign those IPv4 addresses. It was like popularity of internet just boomed. So 2 solutions to that problem were introduced, and one was short term, and it was called NAT, or Network Address Translation, and we will talk about it in a minute. And the other solution was considered a long-term solution, and it was IPv6. And IPv6 has 128 bits just for addressing. That means it has 16 like equivalents of those IPv4 octets. Although IPv6 address is shown a little bit different way. But if we wanted to show it like as an equivalent of IPv4, it would be 16 octets. And now the number of available IPv6 addresses is this. And I don't even know if there is a name for such a large number, but let me just say we should be okay for a while with this number. But let's go back to that IPv4 address and those private addresses I mentioned. I said that the short-term solution for IPv4 was called NAT, Network Address Translation, and that NAT solution assigned 3 ranges of those IPv4 addresses as private IP addresses, and those ranges are, as you can see now. And even though that newer IPv6 address was introduced in 1998, so already over 25 years ago, that temporary, what was meant to be temporary NAT solution for IPv4, for this older protocol, worked so well that it's still the most popular internet protocol even till now. Well, you saw that exactly. I've got only IPv4 address, I don't even have IPv6 address. So let's see how it all works then. And we will explore now how exactly our laptop connects to YouTube and what that private IP address is used for. So what I do first, I type in my laptop in laptop's browser, like something like youtube.com. We already did that, but let me just do it again. So what happens first? Well, first, my browser has no idea where to go, because it needs to connect to IP address, and that name, that youtube.com, it doesn't mean anything to my browser. But, well, you could see that we are connected to youtube.com. So what's going on here? Well, we know already that this is the public IPv4 address for youtube.com, but now imagine if you, instead of typing youtube.com, imagine you have to type in this IP address. 216.58.204. Well, that's fine for a computer, but for us humans, it wouldn't work really. I wouldn't be able to remember IP addresses, public IP addresses of all services that are there. Like maybe I could manage to remember one, but what about the Facebook or YouTube or Google or any other service? They will all have different public IP addresses. So that's why we need another service here in this puzzle. And this service is called DNS. And the DNS will translate that youtube.com, which is human-friendly or easy to remember thing for us, and it will translate it to this public IP address. So when I type youtube.com, first what our laptop will do, it will send that name to the DNS server to figure out what is the actual IP address for that human-friendly name called youtube.com. And if you type that NSLOOKUP, what you do, you run the same process. NSLOOKUP even stands for Name Server Lookup. And it is a query that is being sent to DNS server to give us the IP address for that name youtube.com. And this is the response from DNS server, domain name server, because that youtube.com is called a domain. So basically our browser does the same first. It needs to obtain that public IP address of YouTube from DNS server. And once it has that IP address, it will create something called a packet. And that packet will have computer's private IP address and YouTube's public IP address. That's where those private IP addresses come into play. So how does it work exactly? Well, as I said, when IPv4 address was first created, it was thought that there should be enough IP addresses for all devices in the world. And when they realized that's not gonna be the truth, it won't be enough IP addresses for every single device that will ever want to connect to the internet, they introduced that network address translation. And we can see it here. Our internet service provider will only supply one public IP address for us to use. And that IP address will be configured usually on the wide area network port on the router or any other device that they supplied for us. But now all our devices at home will receive private IP address from one of those ranges of private IP addresses. And each device will get a unique private IP address. And this process of assigning those addresses is called DHCP, Dynamic Host Configuration Protocol. And it's usually performed by the same router, or usually all-in-one device, it's called, that we were given from that internet provider. We call it all-in-one because it's usually not only router, but that DHCP server. It's also access point that, lets us wirelessly connect to that device. So it should be really called all-in-one device. So now, each our device at home will have unique private IP address, but that uniqueness will only be within our home. And in our home, each device will have different private IP address, unique. And that device will be able to communicate with another device at home using that unique IP address. But if we have a neighbor, for example, who has internet access from the same provider, it's very likely that these neighbors' devices at home will have the same private IP addresses as we do. That's because it doesn't matter. Each home on the street can have the same range of private IP addresses, and it's fine. That's because we have NAT service, which will translate our private IP address to public one every time we want to access something from the internet. So let's say my public IP is 12.12.12, let's simplify it, okay? It's just 12s. And our neighbor's public IPv4 address is 23.23.23.23. And then, let's say we both want to go to YouTube at the same time, me and my neighbor. Even though our computers will initially generate the same packet, and this packet will have source IP address of 192.168.1.10, which is within the private range of private IP addresses, and they both will go to YouTube, which is, let's say, 34.34.34.34, just to simplify it. So when the packet reaches the router, those private IP addresses will be translated, hence network address translation, they will be translated to public IP addresses. And from now on, they will differ, because mine will be coming from 12.12.12.12, going to 34.34, and my neighbors will be 23.23.23, going to also to 34.34.34. So once that packet reaches the YouTube, that YouTube server will know they are coming from two different locations. And I keep saying NAT, but in fact there is more than one version of NAT as well, and the one that is used at home is usually a PAT, which is port address translation. There is also like CGNAT and other versions of NAT. I just don't want to talk about NAT for too long, so it's a bit simplified, but hopefully good enough explanation. But going back to our home, that all-in-one device we got from our provider, it will simply know that any packet that has IP starting with 192.168.something, it knows that will be for local traffic, and this traffic has to be sent to a device inside our home. However, when we create a packet that has to go somewhere else, not to 192.168, but let's say to YouTube, which was 34.34.34, so then the device will know the source IP address has to be translated to public IP address, and only then it will be sent towards our service provider. So that source IP address is not translated for communication within our home, it's only translated when it goes out towards the internet. Alright, so the packet reaches our service provider now. So how on earth our service provider knows where to send that packet further? If that device is connected to 10 other devices, how does service provider's device knows where it should send this packet exactly? This is where the magic happens, and that magic is called Dynamic Routing Protocol. And there is many moving parts, but first we will talk about the BGP. BGP means Border Gateway Protocol, and it's a dynamic routing protocol that keeps basically the internet up and running. So how does that BGP work? So BGP is configured on all devices that connect to other service providers. Because on the internet there is no single internet service provider. We might have internet from, I don't know, Virgin Media or Vodafone in UK, but eventually we will have to reach a YouTube server that maybe is connected to Verizon or Cox Communications in US. So BGP will run on all devices that have connections from one service provider to another, and they will automatically, or dynamically I should say, exchange the information about IP prefixes they know. And the IP prefix is simply a bunch of IP addresses. Maybe let's talk about those IP prefixes now. So let's get back to the all-in-one device we received from our service provider. And let's think where that public IP address even comes from. I mean, well, we know the service provider assigned one for us, but where does the service provider get them from? So historically, you could buy public IP addresses from so-called internet registries, like ARIN, like American Registry for Internet Numbers. It's in US, or RIPE, like original internet registries in Europe and parts of Asia. And these organizations used to have public IPv4 addresses available. And if you wanted to get some, you would just make a request and that IP prefix was assigned to you. So that bunch of IPv4 addresses. What you would also get was so-called AS number. It's Autonomous System Number. So once you got that AS number and one or more IP prefixes, you could become a service provider and you could start assigning public IP addresses to your customers, just like you received one from yours. That time is long gone though, because internet registries do not have any IPv4 addresses available. But what you can do, you can still request the AS number, the autonomous system number, from internet registry, and then purchase the IP prefix privately. And there are websites even with auctions where you can buy IP prefixes. And once you have one, you can go back to internet registry and inform them that this IP prefix belongs to you. And when they acknowledge that this IP prefix is part of this autonomous system number, you can start advertising it to other service providers, because that's what it's called, the process. The device is called a router, and the routing protocol will advertise that prefix to other routers belonging to other ISPs. And this process will be propagated until every router in the internet knows that this new prefix belongs to this autonomous system number. And each device will calculate the best route to get to this prefix, to this bunch of IP addresses. And you can even check that online, what AS number your address belongs to. So if we copy our address, let's say AS number lookup. If I type it here, lookup ASN. So this is information about my IP address. It belongs to autonomous system number 206067, and the entire range, it's called AS range, but it's IP prefix I was talking about. So my individual IP address is part of this IP prefix, 92.40.64.0/20. That's a bit outside of scope of this video, but that's simply the IP prefix I was talking about. And this is just one IP out of that prefix. And there is one more thing also I wanted to mention about the BGP, because even though it's considered as one routing protocol, there are really two main protocols involved. And one is called IBGP, or internal BGP, and the other is eBGP, which is external BGP. So internal BGP is a protocol where routers within one autonomous system number will talk to each other, so within one organization, within one service provider network. And the external BGP is a protocol where routers from two different AS numbers will talk to each other. And even though their names are similar, and you would think, well, it's not a big deal, is it? Well, in fact, IBGP and eBGP differ a lot. But okay, that's enough about BGP now. Because in fact, in service provider network, BGP is not the only protocol used. We usually have one more dynamic routing protocol, and it's called Interior Gateway Protocol, like OSPF, which is Open Shortest Path First, or IS-to-IS, which is Intermediate System to Intermediate System, or EIGRP, for example, which is Enhanced Interior Gateway Routing Protocol. And we also have something within ISP, we've got something called MPLS. And it's multi-protocol label switching. So now, what they are and why do we need them in addition to BGP? And the answer is, we need those additional protocols because network within even a single service provider is usually much more complex than those, 4 or 6 routers that are on the screenshots. We usually have loads and loads of devices within that AS number. So as we already know, the routers that connect to other service providers have been configured with BGP routing protocol. And these routers are big, beefy, like very expensive routers, because they have to know entire internet routing table, which means they have to know how to get to every single IP address on the internet. So they cost loads and loads of money, but on the other hand, these devices that you can see inside, that are not connected to other ISPs, they don't have to know any of that. They can be much cheaper, and all they have to do is they have to quickly pass the internal traffic, which means they have to pass the traffic only within that AS number. And the only thing they have to know is what's going on within that AS number, not in the entire internet. So they can be much smaller, much more energy efficient, and much cheaper. Here is the question though. So if a router on the edge that gets the traffic from me, from my all-in-one device, it gets the packet that, let's say, it goes to YouTube. So it goes from 12.12.12.12 to 34.34.34.34. And that big BGP running expensive router knows that the best path is through another device on the other edge of the network within that AS. So then how to pass the traffic there? Because if it will send it to this small router, then as I've just said, that small router does not know anything about those public IPv4 addresses. It only knows how to move the traffic between those routers within the AS number, within the organization. So this is how it works. What will happen is that all those internal routers within the AS number will be configured with private IP addresses on the internal connections. And they will all run different lightweight version of routing protocol, like intermediate system to intermediate system, open shortest path first, or EIGRP. And this routing protocol will only know what is the best path to get within the organization, like from that one router on the edge to another router on another edge of the network. And I think it's also worth to mention that those dynamic routing protocols can also detect any connection failures, and they can immediately reroute the traffic different way so it still gets there, using the new best path that has been just calculated after the outage. So you might think now, well, okay Mark, but the problem still exists. That beefy router still can't pass traffic to that small router, because it only knows about internal IP addresses. So that's where yet another protocol comes into play, and it's MPLS, Multi-Protocol Label Switching. So what will happen, ISP will enable that MPLS protocol on all their devices, and that MPLS will form another way to pass the traffic. What that protocol will do, it will assign some numbers to every router, so it will label them. This router will have label number 1, this one will be number 2, so it will get label with number 2, etc. It will label each device in the network. And then, when this BGP router gets our packet, it will see that this packet has to go to router 6, let's say, that with label number 6, MPLS label number 6. So it will slap that label in front of the packet, and that label will consist just this, the information that this entire packet has to go to router number 6. So this small router now will know how to get there, because it knows this internal network within AS, and it knows where router number 6 is. So this traffic from now on will be passed using those MPLS labels. And once this packet reaches router number 6, that router will strip this label off and will pass it further, this time to completely different service provider, but with no labels, so the packet will look exactly as it did when the first router received it from us. So these MPLS labels will be used only internally, so these small devices can simply pass this traffic. They will know how to pass it. Okay, and that's basically it. That's how this packet is passed from router to router and from service provider to service provider. And each of those big BGP routers will know the best route how to get to a given public IPv4 address, and IPv6 I mean. Alright, so let's talk about the server side now. Our packet reaches the server, finally. So where that public IP address is actually configured on the server. This is a whole different story, because if you just created a YouTube and there is very low volume of traffic, nobody knows about your new service that you called youtube.com, the traffic volume will be very low, so you can have only one server and you can have that IPv4 address or any other address like IPv6, you can have it configured directly on server. And that's fine. If this server will cope with this amount of traffic, it's fine. The problem is when you get more and more users that will upload more and more videos. So what you can think of then, you can think of adding yet another server. But what about the IP address? The fact is, I can create, let's go back here to my AWS account maybe. This is where I can create DNS entry for my server. I've got the domain, it's not youtube.com, but it's automationavenue.com, and I can point, let's say I've got one server, I can assign IP address of 34343434, and this is the first IP address, and this is the only server I have, but then this server, gets more popular, the service gets more popular, and I need to do something about it. So maybe I added another server, but then I have to request another public IP address from my service provider. And maybe they gave me, 45454545. I can assign here more than one public IPv4 address. And now this DNS service would load balance between them. So for example, one packet would go to this one and another packet would go to that one. This way, each server will receive only half of the new traffic from now on. And it looks fine, the first side, but the problem with this DNS solution is that DNS itself cannot see if these servers are fine or they are not fine. So if I added yet another server, let's say 55, 55, blah blah, we've got 3 now already, and the DNS could load balance between those 3. But if one of those servers has any problems, the DNS itself doesn't know about it and will still try to forward traffic to it. So there is a better version actually to deal with high volume of traffic. So let's say we've got the YouTube server or my Automation Avenue server that is getting popular. What we can do, we can create a load balancer instead. And the load balancer will have only one IP address again, only one public IP address, but it will have multiple servers behind it. And these servers will usually have private IP addresses. It's kind of reverted situation to what we have at home. We've got multiple devices going to our router, and then we are assigned just one public IP address. Here on the load balancer, the situation is opposite, because this traffic hits one public IP address, but then load balancer will load balance the traffic between all the servers that are behind it. So one packet will go to first server, second will go to second, etc. But what load balancer also can do for us, it can check what is called health checks. It can run some health checks on those servers, and if one of those servers goes down or stops responding for some reason, or anything else is wrong with it, it will simply stop sending the traffic to that server. And it can alert us, that this server is down or there is an issue with it. So we can go fix it, we can replace the server even, because we can disable it in the load balancer permanently, and then when we have new server, we can enable it again, and it can start receiving the traffic again. What it also allows us to do is we can have smaller servers. Let's say it's a YouTube, yes? The server itself doesn't have to be really that big. The storage behind it has to be big. It has to have large volumes, because think about all those videos that go there. So we can split that and keep it kind of separate from the servers. You build what is called storage area network, and this is kind of similar to what you have at home, like network attached storage, but it will be like at much bigger scale with many more technologies that improve that availability of those hard drives. And you can easily then add new hard drives to that storage area network if your YouTube's website grows larger and larger. You can keep adding those SSD drives, and it's not tied in any way to the workload on the servers. So you can adjust the amount of servers and amount of SSD drives kind of independently, depending on what you need, how quickly your website grows. And this solution might be okay for most of the companies, many companies, but the biggest ones like YouTube or Google, they have to go even further. If we think about YouTube, the fact is that most of the content will be regional. So if I live in Spain, for example, I would most of the time watch Spanish content. If I'm in France, it will be probably in French language, and if I'm in US or UK, it might be yet another different content that is the most popular currently on the YouTube for that particular country. And anyways, pulling all the data from just one location, so if I'm in India and I'm pulling the video from, let's say, US, that also costs money, because it has to travel through entire world, and those connections, like between the ISPs, they don't have unlimited bandwidth, so you have to think of how to optimize it. So what YouTube or other organizations do, they would create multiple locations, like think of multiple of those load balancers with the servers behind them and storage, and then if a user living in France will try to do the nslookup.youtube.com, that user will receive one public IP address of YouTube, but if user in Spain will do the same, or in UK or US, each of them will get different public address. And this IP address will differ depending on the location. And if I go back here to my Route 53, in cloud it's done using Route 53. If you have on-prem, it can be like F5 GTM device, like Global Traffic Manager, but it doesn't really matter. I've got AWS here. I can show you, like we've got, for example, 45454545. You have something called routing policy, and you can see things like geolocation or geoproximity. So what it means, for one domain, like automationavenue.com or youtube.com, you can have multiple IP addresses, and every user will get the IP address that is closest to them based on their geolocation. So if user in France goes to their local IP address, public IP address, on a local load balancer, but for some reason the content is not there, then those servers will pull the content, they will know where the content actually is. And then they will pull from, let's say, a server in US. But most of the time, the content will already be there. So based on how often it's used in a given location, YouTube can move the content, the videos, between those locations, and this way, the videos that are watched most in a given location will be already there, locally. It doesn't have to be pulled across the world. Okay, that was a long journey, wasn't it? But I hope it explains it well, and I know this video was pretty long, but I just hope you finish it with the feeling like, wow, I've learned so much. So let me know in the comments what you think, and I'll see you in next video.